Okay, so today I will be going over Intro to Dynamic Programming. I don't think I'll be able to monitor the chat really, so I'll save questions for at the end, or at the end of every problem, I guess. So the way this is gonna go is I'm gonna go through a series of problems and kind of explain my process of solving these through the different types of solutions that we can use to, well, solve them. So here's the first problem. So think of this as a pinball machine. I think that's what they're called. And you want to travel from the top of the triangle to the bottom and get the largest sum of all the values along the way. So like you start at the 1, and from the 1 you can go either to the 3 or the 5. And from, let's say, the 3, you can either go to the 2 or the 6, something like that. Okay, there we go. Now you can see my mouse. So you can like kind of pinball your way down, and you want to get the largest sum possible. So the first approach that you might think of would be brute force. Try every single possible path. So first go down all the left ones, and then go down all the left ones, and then the right, and then yada, yada, yada. The problem is this is too slow, because if you set the bounds at a certain level, then it's not going to run in time for a competitive programming environment. So let's try a different approach. Let's say recursion. So let's say, so you're going to have this function, I called it calculate, with row and column. So like row would be rows, and columns, I'm calling these like diagonals columns, I guess. So this would be column 0, column 1. This is column 0, 1, and etc. So from each position, you can either go left or you can go right. And so from this position, the maximum sum you can get going from your current position to the bottom would be either the path that goes to the left or the path that goes to the right with the most, okay, sorry, let me back up for a sec. So calc is a recursive function that returns for a given position, what is the maximum sum you can get from this position going all the way to the bottom. So for this, you would either go to the left or the right. So you try and see what the maximum sums are for the left path and for the right path, and then you take the max of them, add your current value, and return that. So that's the intuition behind this recursive function. And then here's the optimization that makes this DP. It's called memoization. Yes, I did not misspell that. It's memoization. So let's say you have this function and you add another 2D array called DP, which is really bad naming, but whatever. And this will hold the values after we've calculated them. So like once you've called like calc 3, 2 once, then you don't want to repeat it, because for any position, the answer is not going to change if you call the function twice, given different starting paths. Like, so if you go along this path and get to 3, the sum from 3 to the ground is still going to be the same as if you took this path to 3. So whatever happened before your current location doesn't affect the answer for this function. So you can just calculate it once and store it. So now you check if this value is not calculated, then you calculate it and store it, and then you return the value. And this way you don't have to repeat and do a bunch of redundant function calls. And this makes your algorithm much faster. Okay, any questions about that? I can see the chat, so if you want to put it there, I'll wait for like a minute, I guess. Okay. Well, I know that wasn't a minute, but it doesn't seem that there are any questions. If there are and you're just typing, then like I'll keep an eye on it, but let's move on to the next problem. This is going a lot faster than I expected. Oh, whatever. So problem number 2. Here you have an array of numbers, and your goal is to find the largest sum of any subset of this array, given that you can't choose 2 adjacent numbers. Like, let's say you choose this 2, then you cannot choose this 1 or this 4. So what would be, okay, so question. What information is needed to calculate the answer for the first I numbers? And let's call this answer DPI. This is another method of approaching a DP problem, or dynamic programming problem. The previous one was kind of like, you could consider an optimization of a recursive solution. This is another way to approach the problem, which is find the answer to the problem that you ask for a certain subset. We should also need, okay, so someone said we should also need whether we took the previous number. Well, if we, okay, if you have another, like, if you know whether you took the previous number, that's not going to automatically give you the answer for this current, like for the first I. If you know that you didn't take I minus 1, that's like just with that information, you can't immediately come up with the solution for the first I. Okay. Yeah, my answer, my question was hinting towards something a little bit different, but yes, that is on the right path. So, well, the answer to my question would be, you need the answers for the first 0 to the first I minus 1. So like, let's say, so just repeating, DP of I stores the answer to our kind of goal for the first I numbers. So let's say you wanted to find the answer for the first 4 numbers, then you would need the answer to the first 1 numbers, 2 numbers, 3 numbers, and then you can calculate the answer to the first 4 numbers. Or else you would have to, like, otherwise you would have to like go back and try to figure it out by like, I don't know, scanning. I'm not sure. I don't think that would work. Okay, so here's another larger example. So this is the mathematical way of writing this, or not mathematical, but like, I don't know, this is like the syntax that I use. So DP of I equals max of previous number taken plus the value of your current index. So let's say you're at 3, then your previous number chosen could be this 1, this 2, this 3, this 4, or this 4, but it cannot be this 1. Oh, right. Oh, I always forget to mention this when I do this problem, but for problems like these, it's also sometimes very, how do I say, convenient to set your state in a certain way. So like, okay, I want the answer for, if you just consider the first I numbers, also assuming that you always take the last one. So like here, what I'm doing is I'm choosing a subset, and then I'm appending our current index to that subset. So I'm assuming that I'm always going to take the last one in my range. Like, and you know that for the entire problem, you might not necessarily take the very last value. So what you can do is just go back and kind of take the max over all the DP values. Sorry, could you repeat the problem again? I think I'm missing something. Okay, so the problem is, what is the maximum sum of a subset, given that the subset cannot contain numbers that are right next to each other. So you can't take this 2 and this 4. So yeah. So what we're going to do is, let's say we take this to reiterate what this means for this kind of description over here is, okay, let's say we're at this 3. So we're going to take this 3, so that gets added to our sum for the current I, the first I numbers. You take the current value, and then you need to choose what's the previous number in this maximum sum subset. Well, it could be this 3, this 4, this 2, or this 1. So that's what this max is taking. And notice that it only goes up to I minus 2 because you can't have the 1 right before it, or else it would be adjacent. So there is another optimization you can make on this. It is always better to choose I minus 3 or I minus 2 as your previous number in the subset. Why is that? Can someone try to come up with something? Or, yeah, you know what, never mind. I'm just gonna explain it. Because they are larger than any other number, they include all subsets. Yes, basically. So if we have, let's say, this 3, we could either take I minus 2, which is this 3, or I minus 3, which is this 4. Now, if we had chosen I minus 4 as our previous value in this array, then we would have chosen this 3, this 2, and nothing else. But we skipped this 3 in the middle. We could always add that 3 back, and that would give us a larger value. I'm not sure if I'm explaining this super clearly. So are all numbers positive? Yes, in this problem, all numbers are positive. Thank you for reminding me about that. Yeah. So because of this, for every index I, we only need to check 2 values, I minus 2 and I minus 3. And so this turns an O of n transition into an O of 1. This means that originally we had to scan through all the elements from 0 to I, but now we only have to check I minus 2 or I minus 3, which is a constant value instead of dependent on the size of the array. And this will make your program, again, faster. Okay, that was problem number 2. And now problem number 3. Again, we have an array, lots of arrays. And this time we want to group the numbers into 3 groups such that the difference between the largest sum and the smallest sum is as small as possible. That's a lot of largest and smallest things. So here's an example of a grouping where we have 1, 2, 4, 3, and 7 in the first group. We have 1 and 2 in the second group, and 5 and 10 in the third group. Do notice that the elements don't have to stay in the order that they originally were. The last group has 5 and 10, but 5 and 10 were not together in the original array. So, let's see. Yeah, order does not matter. No, we need to go back. Okay. So the smallest sum here would be 3 for this group. And the largest sum would be, sorry, I'm really bad at arithmetic. So that's 10, 16, 17. Okay, so this is 17, and this is 3. So the difference between the largest sum and the smallest sum would be 17 minus 3 equals 14. Yes, 14. And so we want to minimize that number, the 14. So how do we do this? This problem seems a lot more complicated, maybe, than the previous two. So this might take a little bit more time. Okay, so let's first iterate in order. By that, I mean try adding the numbers one by one to the different groups. So like, if you think of them as like 3 different bins, then first we're going to try to put 1 in a bin, and then we're going to put 2 in a bin, and 4 in a bin, and kind of go in that order, just to keep things organized, orderly. I don't know. That's how we're going to do this. And then what we might want to notice is one of the key observations for DP as well. What is best now might not be the best later. As in, oh, if I put 3 in bin 1, it's going to minimize the difference for this current setup. But in the future, it might have been better if I had put that 3 somewhere else instead. But we don't want to have to go back and change the way that we ordered the bins, because if we allow ourselves to go back, that's going to make things slower and kind of like make it very confusing as to how we're going to make the decisions in the first place. So this is where DP comes in. If this statement were not true, if you could prove to yourself that what's best now will always be best later, then you don't have to do DP. You can do a greedy algorithm, which is usually going to be easier to implement and also faster. So this statement is kind of necessary or like something that you would try to want to make. This is a statement that you would kind of want to make before you do a DP. So, and here's another thought. If we find all possible sets of group sums, we can find the minimum difference. So let's say, oh, I know it's possible to get a groups of 10, I know it's possible to get group sums of 10, 10, and 12. And then you find like all like possible triplets and like that. Then you can obviously, from that group, all those sets of triplets, then you can find the one that has the minimum difference. So this simplifies our problem a little bit. Instead of finding the minimum difference, all we have to do now is find all possible sets of group sums. If any of this is confusing, please like direct message me in the chat if you want to, because I can't tell if I'm explaining this well or not. Okay, I will continue then. Okay, so, God, this is ugly. We're going to start off with a 4-dimensional array that we call possible. And basically, that's going to mean if sum 1, sum 2, sum 3 is a possible set of group sums for the first I numbers, is there a bound on the sum of numbers? Yes, if this were a proper Yusuko write-up, then there would be a bound on the sum of the numbers that makes this possible. Probably something around 1,000. Yeah, so somewhere around there, I think. I don't know, might have to be less depending on time constraints, but yeah. Yes, that is a statement I will be making later. Thank you for pointing that out. So this is our current this is what we call the state of our DP. A state is like a set of variables, a set of variables that we can use to, DP is dynamic programming, and it is a way of solving problems that can't really be solved through more straightforward approaches like greedy. Yeah, so the state of your DP is like, okay, if I know this, this, and this, I can create a unique scenario that helps me make decisions on what I'm going to do next, and also helps me like locate where I am. For example, in a kind of graph problem, your state might be your current position, your row and your column. Here, our state is how many numbers have we put in bins, and then the sum of the 3 bins. This creates, okay, this isn't a technical term, but a unique scenario. And that kind of helps us make decisions going forward as to what situations can we then transition to, and like, how can that help us find the answer? So this is our like kind of definition of possible. So if possible of I, sum 1, sum 2, sum 3 is, well, possible, if this setup is possible, then the array value equals true. So, okay, so optimizations, because a 4D array, like nothing against it, but it's a little bit cumbersome and not exactly easy to work with, and also is probably going to be very slow and run out of memory. So we're going to have to optimize this somehow. So one given in the for loop. So, and as you'll see later, we're not going to need to refresh our array every single time. We can keep reusing the array. So we don't need I as that first index, because we're already keeping track of it in our for loop, iterating over all of the numbers in our array. And then here's another thing that you can make. Sum 1 plus sum 2 plus sum 3 equals the total sum of the first I numbers. Well, that seems pretty obvious, but because of that, if you know sum 1 and sum 2, and you know I from your for loop, then you can find what sum 3 is without having to keep track of it explicitly, because algebra. So because of this, we can distill our scary 4D array down into a much less scary 2D array. So now we have possible of sum 1 and sum 2 equals true if this configuration is possible. Okay. Now here is some pseudocode to kind of help solve this problem. So, okay, we're going to first we're going to iterate over all numbers in our array, and we're going to try every sum 1 and sum 2 possible. This is why it's also important to have a bound on this sum 1 and sum 2, because you're going to try every sum 1 and every sum 2 possible, like 0, 1, 2, 3, nothing discrete, just try all of them. And if you find that this current setup is possible, like sum 1 and sum 2, then you're first going to try adding your current number. You're going to try adding your current number to sum 1, and then you're going to try adding it to sum 2, and then you're going to try adding it to sum 3, right? So that's what this line does. Possible of sum 1 plus value of I is that new sum 1, and sum 2 is true, because it's possible, like if your current distribution is possible, then you can just add your current number to bin 1. And then same thing with sum 1, sum 2 plus value of I equals true. Now what happens when you add your current number to bin 3? Well, sum 1 and sum 2 don't change. So possible of sum 1, sum 2 is true. Why didn't I put that down? Because if that wasn't true, then you wouldn't have gotten into this if statement. So that would be redundant. Hopefully this makes sense. If it doesn't, please message me saying this doesn't make sense. Going once, going twice. Okay. And that's all I have for you today. Oh my goodness. I was hoping for a little bit of time to answer questions if you had any, but yeah, I guess that's it.